You will recall that value of Hubble's constant was fairly unsettled all the way through 1980s. The reason for this is that these measurements are difficult. There are so many different relations and one has to be calibrated against the other, and there are many opportunities for errors, and systematic errors in particular. And that resulted in values of Hubble constant scattering by a factor of 2, which means the distances would be also uncertain by a factor of 2 and things like luminosities by a factor of 4, and that clearly was not a satisfactory situation. So when the Hubble Space Telescope was launched, measuring Hubble constant was seen as one of its key goals, and it was a subject of a so-called distance scale or Hubble constant key project. This took 10 years of very diligent measurements using Hubble Space Telescope, and even today, Hubble Space Telescope continues to be used for this purpose, improving the results. The idea here was to observe Cepheids in a number of nearby spiral galaxies. And the reason why Hubble was needed is that these stars are faint and they're in crowded fields, so the superb resolving power of HST was needed in order to actually measure their brightness and populate their light curves. Then, using the locally calibrated Cepheid relations, understand the distance to these galaxies, and then use those to calibrate other things, such as supernovae. A choice was made to use the distance to the Large Magellanic Cloud to establish the 0 point of the Cepheid period luminosity relation. You recall that that was the originally discovered period luminosity relation by Henrietta Leavitt, and it still plays a role. And so any uncertainties in the distance to the Large Magellanic Cloud would then map directly into the uncertainties in the Hubble constant. Now, not only did this team perform wonderful measurements, but they're also very careful about their analysis, and they try to honestly account for every source of error they can think of. And the final result is shown here. Hubble constant turned out to be right in the middle of the disputed interval between 50 and 100 kilometers per second per megaparsec. It's 72 plus or minus 3 in just random errors, but also plus or minus 7 kilometers per second per megaparsec as potential systematic errors. And that's an honest result. In fact, this is still perfectly consistent with all of the more modern measurements. Note, however, that there is still dependence on the assumed distance to the Magellanic Clouds, and that is something that people continue to improve. So here is a sample image of what they were looking at. The picture on the left is one of the spiral galaxies used in their study, and superposed on that is an outline of the field of view of the camera of a space telescope that was used. This was the original wide-field planetary camera and has the strange B-2 bomber shape. The picture on the right shows a zoom in on one of those images with some of the candidate Cepheids circled. As you can see, this would be a very hard thing to do from the ground. Some of these Cepheids occur in star-forming regions, so there may well be other bright stars that are blended with them, and that has to be taken care of. And here are some light curves of Cepheids discovered by the key project. These represent many measurements at different times that have been folded together into the best fit period. And you can see that those really look like those of nearby Cepheids. So here are some Hubble diagrams they obtained in the end. The bottom left one shows only that one for galaxies whose distance was derived from Cepheids. The one on the right includes all possible calibration sources they could come up with. And here is a table that accounts for different sources of uncertainty in their measurement. I'm just showing it for information only, and you can see how many things they can think of. And here is their final error probability distribution around Hubble constant. This is actually a good scientific way of presenting result. It's not a number, it's a probability distribution for that number. The peak value is the one that's quoted, and the width of the distribution is indicative of the uncertainty. People continued to try to determine Hubble constant using any one of the number of methods and combinations of different indicators and calibrators, and here is again a table of those. Not there for you to remember all of it, but just to see how much the different measurements scatter around each other. Most of them are certainly within the error bars of the value determined by Hubble Key Project. Now recall that the basis for the whole thing was distance to the Large Magellanic Cloud, which is about 50 kiloparsecs from the Milky Way. So the uncertainty in this distance maps directly in the uncertainty in Hubble constant. And the distance to the Magellanic Cloud was measured in many different ways by many different authors. That alone has a spread of plus or minus 10%. There is maybe about 10 different methods by which this was attempted, and here is the table that shows some of the results. Again, not there for you to remember all of it, but just to see roughly the spread of the numbers and the accuracies that are involved. A more important check, which is actually becoming a very powerful new method, is as follows. In the nuclei of many large spiral galaxies, there is a massive black hole, which for all practical purposes is like a point mass, just like essentially all of the mass in the solar system is in the sun. Now, if we had test particles moving around that black hole, from measuring their orbits, we can find out how far the galaxy is. The orbits can be well assumed to be Keplerian, and the suitable test particles are so-called interstellar masers. These are interstellar clouds that have very sharp line due to the coherent emission, and as they're moving around the center of this galaxy, they can be used to measure the central mass, but also they can be used to measure the semi-major axes of these orbits. This was the first case in which this was done. Since then, there have been more, and the distance to this particular galaxy was found to be consistent with that one determined by the Cepheids. Now, wouldn't it be nice if we can bypass all this messy distance scale ladder climbing from one to another and so on, and go directly in the deep Hubble flow? Well, there are two methods by which that can be accomplished that do not require any other calibration. They're both based on physical reasoning. The first one is gravitational lens time delays, and the second one is so-called Sinyaev-Zidovich effect. Whereas these are based on physics, they're still very much model dependent. Initially, at least, they were producing values that were somewhat lower than that one measured by the Hubble Key project. But since then, they have converged a little more. Any of the small discrepancies can be understood in terms of systematic errors. So first, the gravitational lens time delays. Assuming that we understand the geometry of the lensing, and I'll show this in a moment, we can in principle derive the distance to the lens and the lensed object using the measured time delay. Modeling of the lens geometry is the key uncertainty here, because masses responsible for gravitational lensing are not always perfectly spherically symmetric, and there can be a combination of many potential wells of, say, galaxies in a cluster or a group. So here is how it works. Here is a schematic diagram showing what gravitational lensing might be. There is a background source, say a quasar. There is a foreground lens, which could be a galaxy or a cluster. It bends the light rays coming from the original source, and one usually sees multiple images on the sky. Each of these images correspond to a particular path of light rays that came around the gravitational lens, and they will be generally different in length. The difference in length would translate itself into a difference in arrival times. So if there was, say, some variability in the quasar, we will first see it in one image and then sometime later in the other. These time delays are typically in the range of weeks or months. The path difference between different rays, assuming that you know the geometry, will scale directly with everything else, every other length in the system. And the ratio of this path difference to the distance to the lens or the source is also something that the model will tell you. So by measuring the time delay, multiplying by the speed of light, we directly measure the difference in the path length. And if we knew the lens model, we can then use it to infer the distance to the lens or the lensed object. Sinyaev-Zidovich effect is something entirely different. Clusters of galaxies contain galaxies, dark matter, but also a lot of hot gas that was expelled from galaxies or accreted by the cluster. And since that gas is in the potential well of a cluster, the speed of individual particles, protons, electrons, has to be such that their kinetic energy balances the potential energy. It turns out that that corresponds to temperatures of millions or tens of millions of degrees, which means that that gas will emit in the X-rays. Now we're looking at the cosmic microwave background behind the cluster. The photons of the microwave background will come through, and some of them will scatter off these hot energetic electrons. In the cases of forward scattering, this will generally result in an increased energy of the photon. The energy is being gained from the electrons in the cluster. Of course, there is equal amount going out on the other side. So essentially what you'll see on the microwave background sky is there's going to be a bump that corresponds to this X-ray cloud. And the entire spectrum of the cosmic microwave background will be shifted towards somewhat higher energies. By measuring that shift, we can find out how long was the path, because the longer the path along the line of sight, more chances the photons have to be scattered. Therefore, we can derive from this measurement directly physical linear size of the cluster along the line of sight. We can measure the apparent size of the cluster on the sky, and on average you expect the clusters will have same size in radial direction or orthogonal to it. So since we have observed apparent angular size of the cluster in the sky, and we know how much that is in physical units at the cluster's redshift, we can derive the angular diameter distance. Now, any given cluster is not likely to be spherically symmetric, but the whole ensemble on average will probably work out. A beautiful thing about this method is that it does not depend on the distance to the cluster itself. The source that's observed is cosmic microwave background. The cluster could be nearby or could be very far away. So the method can work over a very broad range of redshifts. There are uncertainties in modeling the process because the gas could be clumpy, there are some density gradients. All of that has to be accounted for before we can derive the actual diameter of the cluster that photon goes through. Next, we will talk about measurements of the age of the universe.